Okay, welcome back. So in this video I'll be talking about the kinetic molecular theory of gases. So this is actually the second part of the series of videos on the states of matter and gas laws. So in the first video I explained to you about the states of matter. So there are three basic states of matter. Just for a simple and a fast reminder, there are three basic states of matter: the solids, liquids and the gases. So I explained about the chemical, the physical and the inspection differences and some similarities between these three states of matter. So I explained about the solids and liquids in a small scale, but I explained about the gases in the large scale when I talked about the gas laws. So that was all about seeing. Right now, for example, if you have a gas law, like Charles' law, you know that when the pressure is constant for a constant mass gas, you know that when the absolute temperature increases, the volume increases in a similar way. So how does this happen, right? So you know that, say you have some sample, right, a gas sample of say 2 cubic meters at a temperature of 290 Kelvin, and you have another gas sample at you increase the temperature up to say 320 Kelvin. So what happens to the volume? So you can calculate that using the Charles law. Similarly, you can calculate using the other gas laws. So how does this happen? Now when you increase the temperature of a gas whose pressure and the mass is constant, you know that the volume increases. But when the temperature increases, how does this volume increase? So that's the concept behind the kinetic molecular theory of gases. So in conclusion, kinetic molecular theory of gases, before I begin this video, is actually the basis of all these properties, all these states of matter, their behavior, they are changing, right? Changes of phases, everything happens, and everything is well described, everything is well explained by the kinetic molecular theory of gases. So to begin with, I have already explained a simple introduction. So to begin with, I will explain you what is meant by the kinetic molecular theory of gases. So the kinetic molecular theory of gases is a model based on a series of assumptions. Now we have actually 5 main assumptions. Now you may have seen in some books and the other sources that there are various assumptions, 6 or 7 or even 8 or 9 assumptions. But actually only 5 assumptions are needed to understand the behavior of gases. So kinetic molecular theory of gases is actually it was presented for gases, but you can even modify this for solids and liquids. It's hard to measure. So in this video I'll be talking only for the gases, right? So not all the assumptions can be used for solids and liquids, some assumptions can be used. So the kinetic molecular theory of gases is a model based on assumptions, and they are used to explain the behavior of the three states of matter: the solids, liquids and the gases. So I'll explain about the gaseous state in this video. Alright, so now some of the viewers who are watching this video might have known what are the properties of matter. So I explained about the properties of matter in the basic concepts of states of matter and gas laws. So for those who have not watched that video, and for those who have watched that video as a reminder, let me explain you about some properties of matter. So in this video, now there are actually various classifications of matter. So in this video I will classify matter according to two ways. So one way of classification, or one method of classification, is based on the internal characteristics, and the other method is using the inspection methods. So the first method, which involves classification of matter based on the internal characteristics, you can classify matter into two parts: the physical properties and the chemical properties. Now to explain this, now you know what are the physical properties and chemical properties of matter. To explain this, I'll take a simple example. Now you know that if I have some sample of water, right? If I put some water into some beaker or glass or something, just a holder, right, a container of glass, a container of water, and you insert, right, or you drawn a piece of potassium permanganate, KMnO4. So you can see after you are inserting this into the water sample that there's actually a color change, right? Now you know that potassium permanganate is violet or purple in color, so there may be some light or dark purple according to the impurities and the other stuff that are inside the KMnO4 mass, right? So for any mass, right, for any sample of potassium permanganate, the color will be light or dark purple or violet in color. So when you insert this potassium permanganate into this water, you can see a color change. Now what happens if you take a sample of potassium permanganate, right? Take a sample of potassium permanganate and you apply HCl, or you actually pour HCl, right? So you know that KMnO4 can be divided into two types, because KMnO4 is actually an ionic part. So into two ions, the potassium ion and the permanganate ion. Similarly, HCl can be divided into two parts: the hydride and the H plus ion and the Cl minus ion, right? So H plus ion contributes to the acidic part of HCl, and Cl minus ion is the anion. So what actually happens when I insert some acid, not HCl, H2SO4, right, HNO3 or any ion, right? What actually happens when I insert some acid into this medium is that this changes its color. Now this not only changes its color, it changes its chemical composition as well. Now you know that although potassium doesn't have many oxidation states, permanganate has many oxidation states. For example, permanganate has Mn2 plus ions, MnO2, which has an oxidation state of +4, or MnO4 minus, MnO4 2 minus, where there are various types, right? Even the manganese 0, right, the metal, right? So there are various oxidation states of manganese. So when you apply, or when you actually pour HCl sample, diluted or conc HCl sample into the potassium permanganate sample, what actually happens is that not only the color but also the chemical composition may change. Now initially it was with the chemical composition of MnO4 minus an ion, but it might go to something like Mn2 plus ion or MnO4 minus, depending on the stuff you add into the sample and depending on the rate and the other stuff of chemical reactants. So due to these changes, the properties of this matter, properties of this KMnO4, not only KMnO4, for most of the matter changes according to various internal characteristics. So color, as I mentioned in the example which I used, potassium permanganate, is a physical property. Another physical property is the molecular weight, volume, pressure. So these are actually tangible things you can see, right? Also these are tangible and you can see this. Now for example, you can see the pressure of a gas being changed when you increase the temperature or when you decrease the volume, right? So you can see that the change of pressure, you can measure it. So these are the physical properties. So the oxidation states, as I mentioned in the case of potassium permanganate, is a chemical property. And also I explained to you about the reactance or the reactivity when HCl is poured into a sample of KMnO4. So that is also a chemical property. So chemical property differs from a physical property in that physical properties can be observed and they can be measured. But chemical properties, although they can be observed, they explain you about the changing of a chemical identity of a substance. Now physical properties explain you about the changing of the physical identity, for example the volume, the pressure, and even the temperature. So those are the physical properties, the physical things that you learn even under physics. So chemical properties are the basis of the stuff you learn under chemistry. So the reactivity, oxidation states, and the other stuff related to change in the chemical identity of a substance fall into the category of chemical properties. So these two properties finally converge to the properties of matter. Furthermore, the physical properties can be divided to two other parts, which are the intensive properties and the extensive properties. So I'll not explain you about the intensive properties and the extensive properties because you already know by one of my previous videos about these properties. So actually this slide and the next slide are actually to remind us for those who watched and for those who have not watched my previous videos and my notes. So the second classification of matter is based on the mode of inspection. So mode of inspection means actually what you see, right? So you can take say a block of wood, right? A block of wood, and you can keep it on a table or any surface. You can see the differences. You can take a gas sample, you can apply pressure, you can increase the volume, you can decrease the temperature, you can do various stuff, you can see what happens. So those are actually the macroscopic properties. So the macroscopic properties are the properties that we have been talking so far in the concepts of states of matter and gas laws. So for example, mass, volume, pressure, all those are macroscopic properties. So another type of properties is the microscopic properties. So microscopic properties are properties that can't be viewed from the naked eye, because the behavior of the microscopic elements, for example the behavior of atoms inside an element, cannot be seen through the naked eye, right? So what happens is that now for the mass to change, or for the volume to change, the atoms inside this element should change. So microscopic properties are actually a subset of the macroscopic properties, and microscopic properties are used to explain the changes of the macroscopic properties. So microscopic properties form the basis of the behavior and the changes that happen to the macroscopic properties. So I explained you about the macroscopic properties in my videos on the states of matter and gas law. So there are various properties that we learned under behavior using graphs, using sample problems, and using various other laws and their derivations, right? Various concepts we learned. So in this video I'll be focusing on the microscopic properties. So microscopic properties is actually the basis of kinetic molecular model. So the kinetic molecular model has been presented to explain these changes that happen to the microscopic properties. And due to these microscopic properties, as I explained, these microscopic properties form the basis for the macroscopic properties. So finally, the kinetic molecular model has been presented to explain about the changes and the behavior of the macroscopic properties that you have already experienced. Alright, so having explained about a brief introduction of the kinetic molecular theory of model and gaining a relationship between the kinetic molecular theory and the macroscopic properties using the microscopic properties, let me explain you now the common kinetic molecular model. Now you need to know about the kinetic molecular model before going for assumptions and explaining the behaviors of the states of matter and the gas laws using the kinetic molecular model. So the common kinetic molecular model is actually explained, right? Is actually used to explain the three states of matter, how the three states of matter exist and the difference between these three states. Now according to this model, all states of matter are composed of molecules. You have to assume that. So that's actually not an assume. We don't consider that as a main assumption of the kinetic molecular model. So we assume that as it is used, the molecules are the basis of all states of matter. So don't think that this is a main assumption of the kinetic molecular model. This is just a minor assumption, right? So the velocity of particles in a gaseous medium is greater than that in a liquid or solid medium. Now I am going to explain you about the phase changes, as to how the phase changes of the gases, the solids and the liquids can be explained using the kinetic molecular model. So because this forms the basis, so this forms my basis of explanation on the kinetic molecular model. So when you think about gases, solids and the liquids, you know that when heat is provided to a solid medium, at some point you know that when the binding energy is greater, at some point when the molecules are moving with the greatest velocity, we can see that it follows that the temperature of the medium will increase, and when more and more heat is provided, when the vibration of matter increases and when the bond energy increases, you can see that at some instance at the melting point, you know what is the melting point. At the melting point, melting occurs and the solid converts that to a liquid. Similarly, at the boiling point, when the molecules inside the liquid vibrate with the maximum frequency or the maximum frequency, or we call that the amplitude, right? You can see that at the boiling point, so that is at the boiling point. For water, you can see that is 100 degrees of Celsius or 373 Kelvin. At the boiling point of any liquid, it gets converted to a gas. So in the case of the gaseous medium, the distance between two molecules is larger than that in a liquid and the solid mediums. So the attraction potential or the attraction between the two molecules is small. So this actually is one of the assumptions that I will be explaining you in the later part of the video. So the phase conversion, so the phase changes that we have already studied under heat and the other concepts related to chemistry, it can be explained using the kinetic molecular model. So using the kinetic molecular theory, you can explain the differences, or it can be explained. It uses these concepts: the shape, volume, density, compressibility, diffusion, rigidity, right? Even the shape, the volume and the density are important, or volume and the density alone necessary. We don't actually need all these, right? Even these two are sufficient to explain about the kinetic molecular theory of gases. So we use normally some physical characteristics like this to explain about the kinetic molecular theory. And one of the other great thing, right, to explain to you is that the pressure of a gas is actually due to the force, right? You know that by definition pressure is the force per unit area. So forces happen when these molecules get collided with the wall of the container in which the gas is stored, right? So the gas molecules actually exert a force on the container. Now assuming that the container doesn't increase its surface area, right, within the range of time we are taking into account of the pressure, you can say that the pressure is directly proportional to the number of collisions. Now you know that the number of collisions is actually due to the momentum. Now you know that if you have a greater momentum, that means you have a greater velocity, because the mass of a gas molecule or a gas particle doesn't change. So the momentum is directly proportional to the velocity of the particles. If the velocity is high, the momentum will be high. If the momentum is high, the number of collisions will be high. If the number of collisions is high, the force exerted on the surface will be high. And if the force is high, you can say that the pressure is high. So finally, pressure has a direct relationship with either the momentum or the velocity of particles. So this is another assumption of the kinetic molecular theory of gases. Now, having explained about some assumptions in small scale about the kinetic molecular theory of gases, let me come to the topic of the main assumptions of the kinetic molecular theory of gases. So actually these assumptions are the basis of the explanation of the change of characteristics, the behavior of molecules, and the other stuff related to the changes that take place, the visible and the invisible changes that take place inside the three states of matter. So the first assumption is that the gases are composed of rigid spherical molecules, right? Spherical molecules, and the size of such molecules are very minute in comparison to the distance between two molecules. So what I mean by that is that now gas molecules are very small in size, but the distance moved by them within a unit time, you can say, is very large compared to the volume, right? So you can think these as very small, like grains like things, and even smaller than grains, but we can assume that as in comparison to the container in which they contain, these are like small grains, right? Small grains, and you have a large container, but you have small grains that travel with actually a large velocity. So you can see that when these small grains or small molecules of gases are moving with some velocity, compared to the volume of the gas molecule, the volume of the container in which the gas is contained is greatly high, right? It's high. So you can say that the majority of the volume of a gas is not occupied by molecules, right? So the majority of the space is free, right? So that's about the first assumption of the kinetic molecular theory of gases. The second assumption is that the gaseous molecules travel in linear paths in various directions. Now you already know about that. I explained that in one of my previous videos on gas laws, and also when I was talking about the differences between the different states of matter. So actually that's also considered as an assumption of the kinetic molecular theory of gases. And also what is important here is that not only the assumption, but when these molecules travel in linear paths in various directions, what actually happens here is that the qualities or the characteristics that depend on this movement, such as the pressure. Now I explained to you what is the pressure of a gas, right? How pressure occurs. So since the gaseous molecules travel in linear paths, the pressure will also act in a proportional direction. So the assumption that gaseous molecules travel in linear paths is important when considering the pressure and the other physical characteristics that depend upon the direction of travel and the force exerted, and the other basic changes that take place inside a gas sample. So the third assumption is that the attraction and the repulsion forces are negligible, right? So attraction and the repulsion forces between two molecules can be ignored because they travel with a very large velocity. They don't have time to attract between them. Now in the case of solids, you know that the distance between two molecules is very small. In a liquid it has a medium distance between the molecules. So in a gas it has the least distance between the molecules. And also in the case of gases, the molecules travel with a large velocity. So what happens is that since the distance traveled within a unit time is large, you can assume that there is no interaction or the attraction or the repulsion between these molecules. There is no time for these molecules for the attractions and the repulsions. They just go away, although they can meet and they may collide with each other, right? They may collide with each other. We cannot assume or we cannot consider those to be attractions and repulsions. Those are completely due to, we assume that those are completely due to the collisions that take place when they travel in linear paths, right? So there may be collisions. We can't say that there are no collisions, right? There aren't any collisions. So there may be collisions, but those are unlike in the case of solids and liquids. Those are not due to. We assume that those are not due to the attraction or the repulsion or the interactive forces, the intermolecule and the intramolecule forces between these molecules. In accordance with the Newton's laws, until the collision takes place, you can say that the molecules, right, they travel in linear paths and the molecules exert equal and opposite forces on one another. So that's actually about the linear momentum concept. When some collision takes place, say a force of F is exerted on one molecule on another, the same force, according to Newton's third law of linear motions, you can say that the force exerted on the other molecule is equal in magnitude but opposite in direction, right? So that's about the action and the reaction as explained by the Newton's third law. So the fourth assumption is that the collision between these are completely elastic. So you know that what are meant by elastic collisions. So elastic collision, in the case of elastic collisions, what happens is that the kinetic energy loss of the system is zero. Now if initially the system has total kinetic energy of 120 joules, right? For example, 120 joules, this might convert into various formats, but finally, if you measure the final kinetic energy at any instance, you can see, right? You can observe that the final kinetic energy is also that 120 joules, right? I just took an example. So what I mean by that is that if some kinetic energy is lost somehow, the kinetic energy is gained by the other molecules. Now say there's a collision between two molecules, some 20 joules or some joules of kinetic energy is lost, and that energy is gained again or regained by two or more other molecules, right? So they always keep the kinetic molecule, actually the kinetic energy, the difference of kinetic energies to be zero, right? So the collisions between these are completely elastic. So that's the fourth assumption. So the last assumption is a direct relationship between the kinetic energy of a gas and the absolute temperature. So we say that the mean kinetic energy of any molecule, hence the system of molecules, is directly proportional to the absolute temperature. Now you know that when we increase the velocity, right, when we increase the temperature of a system, we increase the velocity. So I'll explain that in another video, right? So in this video I explained about the assumption, so I'll explain about the behavior of these molecules depending upon the assumptions we built up in this video in another video. So we assume that we can show that when the temperature, the absolute temperature of a gas increases, the velocity also increases. So when the velocity increases, the square of the velocity should increase, and since the mass is a constant, the Ke or the kinetic energy increases. So finally the absolute temperature makes the kinetic energy increase. So the temperature, the absolute temperature, has a direct proportionality to the kinetic energy, right? So it also follows that molecules tend to be stationary or move with constant velocity when the temperature is unchanged. Now we can say that if the temperature is changed, now this is very analogous to the Newton's first law of motion. When there is no external force, the objects don't travel. Similarly, when the temperature is not increased, the molecules have constant kinetic energy and hence a constant velocity and a constant momentum. So the force exerted is constant, hence the pressure is constant, and when the temperature is constant, the volume is also constant. So those will be explained, and the behavior of the gases and how they behave will be explained in another video on the series of videos on the kinetic theory of gases and the states of matter and gas laws. So in this video I explained to you about a brief introduction and the assumptions of the kinetic theory of gases, also called the KTG. And thanks for watching this video, and I hope that you will join with me to watch the next video on the behavior of kinetic molecular theory of gases. Thanks for watching this video, and see you soon.